Good morning, students. Welcome to another session of distributed generation and smart grids. In the last session we were discussing about Micro-CHP systems. We had discussed about various technologies used. We had already gone through IC engines and Stirling engines, and today we will see microturbines and fuel cells. So you can see the line diagram of a microturbine. They are small simple cycle gas turbines. The inlet air is compressed, and this air goes to a recuperator and it enters a combustion chamber. The fuel also reaches the combustion chamber, and here combustion takes place. Then either steam or the hot gas enters the turbine, and the turbine is rotated, which is coupled to a generator, and the generator produces electricity. The turbine outlet hot air goes to the recuperator, and this heat energy can be partly used for heating the inlet air, and remaining goes as waste heat. The outputs of the microturbines range typically from around 25 to 300 kilowatts, and their efficiency, the thermal efficiency, is increased using a recuperator. So the waste heat is used for heating the incoming gas. So microturbines are available in two forms: single shaft or split shaft units. This is a cross-sectional view of a microturbine. Different parts I have already explained to you now. So once again, the main part is a turbine, normally a high speed gas turbine. Then this turbine is coupled with an alternator, and there is some power electronic devices. In single shaft machines, the frequency is very high, typically from 1500 to 4000 Hertz. AC voltage generated by the alternator has to be converted to 50 Hertz. So we need some power converters. Then recuperator recovers the waste heat to improve the energy efficiency of the micro turbine. And the fifth and the last is the control and communication, turbine control mechanism, inverter interface, starting up electronics, instrumentation and signal conditioning, data logging, diagnostic and user control communications. So in a single shaft micro turbine, the turbine is directly coupled to the generator. You can see the turbine is directly coupled to the generator, and the output of the generator is rectified and then again inverted, and we get the output. So typically the speed is in the range of 50,000 to 120,000 RPM. The alternator also has to rotate at this particular speed because they are mounted on the same shaft. Most microturbines use permanent magnet synchronous generator or asynchronous generator for power generation. Now this PMSG, high speed PMSG, has many disadvantages, such as thermal stress. So it undergoes a lot of thermal stress, demagnetization phenomena, centrifugal forces, rotor losses because of fringing effects, and high cost. The disadvantage of coupling induction generator is that though they are cheaper and robust, their speed is load dependent, and they cannot be connected to the grid without the use of expensive power conversion systems. The use of power electronic interfaces introduces a lot of harmonics in the system and reduces the output power quality. Now these disadvantages can be we can avoid these disadvantages by going for a split shaft microturbine. So here we are using a gearbox to reduce the speed so that the output is directly 50 or 60 hertz. So the advantage of coupling NSG with a split shaft microturbine is that it eliminates the use of power converters. So the generator is connected to the turbine via gearbox to generate directly 50 or 60 hertz power. The main features are it can supply a customer's base load requirements, or it can be used for standby. Peak shaving applications, what is peak shaving we will see in a different module, and cogeneration applications. And the size is very small compared to other DERs. The efficiency is almost more than 80% if we use the waste heat. The emissions are lower than 7 ppm for natural gas types, and it has a good life of approximately 45,000 hours. And it is economical, fuel flexibility is there, noise level is acceptable noise level and vibrations also, and the installation is simple. Now we come to fuel cells. There are different types of fuel cells. Basically every fuel cell converts chemical energy into electrical energy. So it consists of two electrodes. One is called an anode and another is called a cathode, and there will be an electrolyte. So just like any battery, there is an anode, there is a cathode and an electrolyte. The reactants and the products are not stored like in a battery, but they are continuously fed to the cell. During the operation, the hydrogen rich fuel and oxidant, usually air, are separately supplied to the electrodes. You can see here the fuel is supplied from this side to the anode side, and the air is supplied to the cathode side. So electrochemical oxidation and reduction takes place at the electrodes, just like in a battery, to produce electricity. So heat and water are produced as byproducts. So water comes out and also heat comes out. These are the two byproducts. Now a single fuel cell can supply a voltage less than 1 volt. So you need to connect many fuel cells in series to get a higher voltage. So let us see different types of fuel cells. The first one is proton exchange membrane fuel cell, or PEMFC, and it operates normally at around 80 degrees centigrade. Now this type of fuel cell, they are portable, and mostly they are used for portable fuel cell applications. They operate normally between 50 to 100 degrees centigrade, and mainly it can be used for transport applications. So they are mainly used for transport applications. The next is PAFC, or phosphoric acid fuel cells. As it's shown here, the operation is at 200 degrees centigrade. It was first developed in 1960s, and they are good candidate for stationary applications. The next one is molten carbonate fuel cell, or abbreviated MCFC. They operate at temperatures of 600 degrees centigrade and above, and they are currently being developed for natural gas, biogas and coal-based power plants for electrical utility and military applications. And the next one is solid oxide fuel cell, or SOFC. They are characterized by their electrolyte material. So SOFC has a solid oxide or a ceramic electrolyte, and they operate at around 1000 degrees centigrade. This is a news article dated 13th March 2018 in Financial Express. ISRO and Tata Motors combinedly they are developing India's first fuel cell bus. So it is a zero emission mass transport solution, and they developed in partnership with the ISRO. So combining hydrogen gas and oxygen, the fuel cell produces electricity to power the electric motor with water and heat as byproduct. These are the references. Please go through them to enrich yourself. And with that, we finish today's session. Thank you very much. This is Dr. Unnikrishnan PC signing off.